So, hello guys, a rigid body. Let's quickly talk about a rigid body. Don't forget to like and subscribe, and you can join my channel membership. Just click the below of the video, click on the button join. It's just 1,000 naira per month to have access to explicit and intensive class, an explicit video. Thanks for watching. Now, a rigid body is a body a body whose particles remain at fixed distances from one another, even while in motion, even while moving or while in motion. Now, a body is rigid when the particles of that body is at fixed distances to each other, even maybe it's in a state of rest or it's moving. For instance, this is a rigid body. Whether it's in a state of rest, the distance of the particles of this body is not changing, and even whether it's moving, the distance is not changing. Now note the distance. I can make the distance to change if I change the shape. You can see that initially it was a pure rectangular shape, right? But now I change it to something like, can you see now? So this denote that some or even all of those particles have changed their distances from each other because I bend this thing. The particles eventually, you may not see it, but the distances are changed. But if I leave it this way, even though it's moving, the particles remain the same. So when we say whose particles remain at fixed distances from one another, even while moving, this statement denotes that the shape and size of such body do not change. Yeah, the shape and size do not change, because if it changes, then the distances of those particles from one another will not be fixed. Examples of a body that are not rigid, like gas, like liquid. Because as liquid moves, the shape or the size begins to assume the path is taken. Do we get? As gas moves, the shape differs, like it moves randomly. But for solid, most solid or all solid, they are rigid body. Take note about that, please. I hope that's clear enough. Now let's talk about rotating body. Now, or rotating motion. Let me say rotating motion. Or before then, now let me give few examples of a rigid body. A rigid body, we have what? A metal rod, we have a wheel, um we have a disc, we have sphere, we have holosphere, and more like that. We have many rigid body that you can mention. So these are examples. Now let's talk about rotating motion. Rotating motion, it means means let me say, I'm looking for a better word to use there. Okay, no problem. Let's just say motion about a fixed point. It means motion about an axis or a fixed point. Yeah, like example, we have a ceiling fan that is rotating, and we also have a car tire rotating, and we also have the spinning of the earth, the rotation of the earth about its axis, the earth spinning. So these are examples of rotating bodies. Are we together? So in rotational motion, every particle, let me write it here. In rotational motion, every particles of such body moves in a circular path about the axis. Take note of that. Every particle of such body moves in a circular path about the axis. So this can denote that all rotational motion can also be circular what? Circular motion. But note, not all circular motion are rotational. Yeah. A circular motion, that a motion that forms a circle. But it may not be rotational. For instance, a round and go. Not, we call it roundabout, but you don't keep on rounding it about. You round and you go. It's a round and go. Maybe a car is moving because the round and go, so the car can move in a circular motion about the round and go. But because the car is not rotating, for the car to be rotating, that means the car, do we get? Maybe the car is rotating like this, and as it's moving. But it's possible for the car not to rotate and yet move in a circular pattern. So not all circular motion are rotational motion, but all rotational motion also involve circular motion. Yes, I think that should be correct. And if there's anything to add there, probably in the comment section. So every particle of such body moves in a circular path about the axis. About the axis. About the axis. Take note of that. So when the body is rotating, like when the whole body is moving about a fixed point, automatically there is a formation of circular motion about that axis. Do we get? It's about that axis that the circular motion is formed. But a body can be moving in a circular motion, not about any axis, and yet it's not rotating. Now let's keep that aside. That's not our business for today. Now let's talk about moment of inertia. Moment of inertia, let me call it the rotational equivalent of mass. Like the rotational. Though I'm still going to define it in another way. Just keep this. The rotational equivalent of mass. The rotational equivalence of mass. Now take note of this thing. Now in linear motion, mass of a body under linear motion, is a moment of inertia is rotational equivalent of mass. Then I'm still going to give us another definition. But note, in linear motion, mass of a body tells us how difficult it is to change motion. Let me say, mass of a body tells us how difficult it is to change the motion of such body, to change motion. That is in linear motion. But in rotational motion, in rotational motion, you know what happened? In linear motion, mass tells us how difficult it is to change motion. But in rotational motion, instead of mass, moment of inertia tells us how difficult it is to change rotation. In rotational motion, moment of inertia tells us how difficult it is to change rotation. I hope that thing I gave, I hope is very, very clear. Please take note of that. All right, let me clean. Now let's move on. Now, I said earlier I'm going to give another definition of moment of inertia. So moment of inertia, initially I said is the rotational equivalent of mass, which is very correct. Also note that moment of inertia can also be defined as to be the sum of each particle. Moment of inertia of a body can also be defined to be the sum of each particle's mass. For a body, we have many particles inside that body. So the sum of each mass of the sum of the particle's mass, the sum of every mass of the particle times sum of each particle's mass of that body multiplied by the square of the radius, the square of the distance rather, square of, or let me say, of each particle's distance, square of particle's each particle distance from the axis. So in a nutshell, you can say moment of inertia equals to mass times r square. But because we have multiple particles inside that body, let's say m1 r1 plus what? m2 r2 square plus m3 r3 square plus dot dot dot, as the case may be. So like summation of the total mass and the total distance from the axis, like total distance of each particle from the axis and the total mass of each particle. The square of the distance times the mass. Do we get that now? So now let's talk about moment of inertia of a point mass. When we are talking of a point mass, that one is just like just I equals to mr square of a point mass. That is, when we are talking about a particular mass, this is just it. So let's not waste much time on that. Now, some examples of moment of inertia of bodies. Let me say the first one. Let's talk about the like examples of moment of inertia of a body using different types of body to denote it. For the first one, let's say we have a uniform meter rule, or a uniform thin rod rather, that is rotating about an axis through its center or its middle. Through its center or middle. Now I want to prove formula. So take note. So let's say this thin rod is rotating about this middle. So here, so let's just listen. So we take this place to be the origin, since that's the place it's rotating. So assuming this axis, so this gives us, this L over 2. So let's say this is negative x, this L over 2. Let's say this is positive x. These are half half. So since this place is origin, the center, that's where it's rotating, is origin. We can take just half, is 0 and L over 2, or is 0 and L over 2. Do we get? Or minus L over 2 and 0, anyone. So if we take 0 and L over 2 as our limit, that means we are going to multiply our final answer by 2, because we are only dealing with half. But if we want to deal with the whole of the ruler, then we take negative L over 2 and L over 2. I'm using axis to differentiate it, that this should be taken as negative, this should be taken as positive. Do we get that? And we have our what's it called? Let's say for a small change in length here, let's say from this place to this place, we can call it our dx. Yeah. So let's say our lambda now equals to dm over what? Over dx, which is what? Mass per unit length. Are we together? So I just call it a particular stuff. I just call it lambda. So our mass per unit length, or change in mass over change in distance, which can be replaced as this. So we also have what? Now if you cross multiply for this one, so we have change in ml equals to what? M dx. So now our change in m equals to what? Equals to m over l dx. If I make this guy the set of the formula, I will get m over l dx. These are the two things you need to know initially, that there is a change in m over change in distance. Your mass per unit length, which is also equal to mass per unit length. Cross multiply, you get this. So you get this. In your exam, I think it's going to be OBJ, so they won't ask you to prove, just know the formula. But in case you forget, you can prove it. So let me write this. So we have our change in m equals to m over L dx. Let's keep that. So don't forget that our change in inertia is same thing as what? Change in m L square. No, I gave us a formula for inertia initially that I equals to what? mr square. So our r is like x here. So since we have change in I, it's change in m. Is that clear? So there's no big deal about that. Now, I think yes, I want to do a substitution now. Okay, now our change in inertia equals to change in m. What's change in m here? Instead of writing change in m, we write what? ml, right, dx multiplied by what? S square. So our change in inertia equals to what? M over L rather, S square what? Dx. Do we get that? Yeah. So this is where we stop. So now if we integrate, change di equals to what? Integral of what? M over L S square dx. So this like the derivative of I. If you integrate it, it will give you I equal this constant m over L integral of S square dx equals to m over L. If you integrate S square, you get S cube over 3. Don't forget, you can use 0 and L over 2 as your limit. But when you use that one, you will multiply by 2 because you are only dealing with R. But if I want to deal with the whole meter rule, I will use negative L over 2 and what? Positive L over 2. And I won't multiply by 2. We get the same answer. So, uh, so now, let's substitute our limit. So we are going to have our limit. Uh, 0 and L over 2 is 0 and L over 2 is 0 and L over 2. So here now we have m over L s cube. If you put L over 2 all cube divided by 3 minus m over L over 2 sorry is 0 cube over 3. Let me check. Yeah, I hope it's clear now. Instead of x, you put the upper limit. Here you put the lower limit. All this one returns to 0. So let's focus on this. So this guy gives us m over L cube. We have L cube, 2 cube, that's 8, times 3. Are we together? So at the end of the day, we have what? We have LN1, LS2. So we have ML square over 24. So is that clear now? This is for half times 2. So we have ml square over what? Over 12. This is the moment of inertia for a thin rod that is rotating about an axis through its center. If you are using 0 and L over 2 as your limit, multiply by 2 at the end of the day, because that means you are dealing with half of it. But if you want to deal with the whole without multiplying by 2, just use your limit as negative L over 2 and upper limit as L over 2. You still get ml square over 12. Take note of that. Now the next one, when same rod, this same rod now, let's say it's not rotating through it's rotating through one end. Maybe it's rotating through here or through here. So we are using 0 and L rather than L over 2 because it's the whole part now. It's rotating through one end, not through center. So what we are dealing with now is that our integration now will be from 0 to L of that same formula that we did earlier. It's m over L S square. So our R equals to still that same thing because we are still dealing with the same meter rule, dx, the same T rod rather. So if you integrate this guy, our limit is 0 and L. If you integrate this, you get S cube over 3. Put L, we have L cube over what? Over 3. Don't forget there is m over L outside. I'm trying to check something. Yeah. So yeah. This m over L is constant. If you integrate this, you get S cube over 3. So we have m over l, put l for x here, minus m over l, put 0 for x here, is 0 cube over 3. All this will turn 0. L here 1, L here square. So here we have ml square over 3. ml square over 3. So when a thin rod rotates about its axis at the center, you have over 12. At one end, you have over 3. Just take note of those formula. They are very, very much important. So let's talk about circular discs. A circular disc rotating through its center. Note, a circular disc is like a ring. Yeah, this is how it is, like a ring, but this one is flat. It doesn't have, though it has thickness too, but not that long like a real ring. So circumference of a circular ring equals to 2 pi r. So let's say 2 pi x altogether, and the thickness equals to dx. So an area will give us a circumference times thickness, which is 2 pi x times dx. So the area equals to 2 pi x dx. Don't take them. Take note of that. We also know that normally area is always pi r square. Are we together? So whereas our mass per unit area, or per unit area is going to give us, let's call it what is the name of this guy? So yeah, surface mass density. The surface mass density of a circular disc, I think is this sign, is known as the mass per unit area, which is m over pi r square. Are we together? So where this one means the surface mass density. So now if we find, because this guy is like change in area, this formula that we derive, because there is a dx here, this for change in area, this for, so this total area, and this mass per unit area. So let's say our change in mass over 2 pi over change in area, which is 2 pi x dx, equals to mass per unit area pi r square. So this is where we are actually going to. This is what we want to derive. So let me write it up here. Over 2 pi x dx equals to m over what? Pi r square. So now let's make dm the surrogate of the formula, this guy. So if you cross multiply here, we are going to have dm equals to m over pi r square. If this comes, multiply by what? 2 pi x dx. Pi can cancel pi. So we have dm to be, dm or change in m to be what? 2 times m, 2m. Then we have what? X what? Dx over r square. 2m over r square. There's a r square here. X dx. So, and don't forget that di, what do I mean by di? Our change in inertia equals to what? S square what? Dm. Can we see the beauty of what I'm already seeing now? This is 2m x dx. So instead of dm here, all the d, dm is equal to this. So our di equals to s square. What's our dm? All of this, because this is dm. 2m x dx over what? R square. So now 2m over r square is a constant. Let's say our di equals to 2m over r square. S square times x. s cube then dx. Now integrate. If you integrate this, you integrate this. This a constant can actually come out. Are we together? So because this is a part circular disc, we are taking our limit from 0 to r. 0 to r like this. Let's say from we are taking this place to be origin, and with the whole length of the radius 0 to r. So that's our limit. So if you integrate what you differentiate, the I means differentiation of I, it will give you I back. So you have 2m over what? R squared. If you integrate s cube, you get x4 over 4 is 0r. So now if you substitute r into this, if you substitute r, we have what? Our I equals to 2m over r squared. Put r, we have r4 over 4 minus, if you put 0, everything will turn 0. So 2m over r squared is 0 is power 4 over 4. All this one will turn 0, so we don't need it. So this one cancel to out of this, we have 2r left. 2 here 1, 2 here 2. So we have m times r squared. This r squared, this r4, it cancel to remain r squared. M times r squared. R equals to r squared. We have m here over 2. So for a circular disc, the formula is mr squared over 2 is same as 1 over 2 mr squared. You can cram it. For a thin rod that is about the center, that the motion that its axis is about the center, 1 over 12 mr squared. That at one end 1 over 3 mr squared. Circular disc 1 over 2 mr squared. Continuous like that. Please take note of that. So those are the formula. So let me just write some of those formula. For a point mass, I equals to mr squared. For a thin rod about its center, I equals 1 over 12 ml square. Sorry, it's ml square. I wrote r square to the one I just cleaned now, ml square. So let's say for the same thin rod about one end, same thin rod about one end, not about center now. I equals to 1 over 3 ml square. Now for a circular disc that we just did, we have 1 over 2 mr square. For a holosphere, or let me say holo ring, for a holo ring, we have I equals to mr square. For a solid sphere, we have I equals to 2 over 5 mr square. Is that video still showing? Okay. For a holosphere, we have I equals to 2 over 3 mr square. Solid is 2 over 5. Holo, don't forget, holosphere is different from holo ring. So these are the formula you need to know, and we've proved some of them, so we don't really have time. So now let's treat two questions. Let's quickly treat two questions before we call it off. So looking at this question now, you should know that this is about a point mass. Moment of inertia of a particle mass. This is a point mass. So our m equals to 5 kg. Distance equals to 4 meter. So for a point mass, you know I equals to what? M r square or ml square. What's our m? 5, 4 square. And that's 5 times what? 16. That's what? 80 kg per meter square. 80 kg per, no, sorry, not per meter square. 80 kg meter square. 5 times 10, 50, 5 times, yeah. That's the moment of inertia for that particular particle. Now, another question. A thin rod of mass 6 kg and length 3 meter rotate about its center, not about its one end. If it's about its one end, we are using 1 over 3 ml square. But about its center, what are we going to use? 1 over 12. So note the difference. All those, know the difference, know what the question is asking you. Don't just use any formula anyhow. So each condition or each rigid body with specific condition has its own unique formula of application. So here we are 1 over 12 multiplied by our mass is 6 kg times what? 3 square. So here we are 1 over 6 here 1, 6 here 2. So here we are 1 over 2 times what? 6 here 1, 6 in 12, 2. So we are 1 over 2 times what? Times 9. 3 square is 9. 9 divided by 2. So our inertia is what? 4.5 kg meter square. So that's that for that. See you in the next video. Don't forget to like and subscribe, and please share the video. Drop your comments on the comment section. By doing so, you are promoting the channel. I love you. See you in the next video. And you can click on the join button below the video to subscribe to my channel membership. Thank you. I love you.